we're going to talk about is inverse functions. Inverse functions. And one of the things that I really like, I find it an advantage, even though these classes, the two that we're taking, that y'all are here with me for, right? Pre-Cal and Cal 1, even though it's just lightning speed, getting it all in, we at least, since you have me, we know, I know what I've covered in the first 8 weeks. So I know that you know about inverses, right? We don't have to kind of go over it too much because we just covered it. And I know that we just covered it. But I do want to talk about very briefly inverses as well as their derivatives. Because again, the highlight of this particular section is more about trig inverses as opposed to just inverse, the derivative of inverse functions. So when we think about an inverse function, right, we have said that if I'm talking about a function f and I plug it x into the function, it's going to map over here to its y value, right? When I put x into the function machine, I get back y, correct? All right. And because we are talking about inverses, if I were to put a value into the inverse, I go right back to where I started from. That's the nature of inverses and their functions. Remember, we talked about log and exponents are inverses of each other, right? Okay, and so one of the properties of inverses, and I'm just going to say, all right, so we're going to say we have our function f of x, and then its inverse f inverse of x, which we're going to identify as g of x to get rid of some of that, the x in there, okay? So one of the properties that we know from inverses is if I compose one with the other, so in other words, if I have g of f of x, that gives me back x, right? That was a property of inverse functions. When I compose a function with its inverse, I get back x. And it was the reason why we were able to solve sine equations, right? Trig equations, is we were in essence taking the inverse of both sides because it gives me back the argument. So if we want to now put this in the idea of derivatives and in calculus, if we start with this rule that we know, or this property that we have right here, g of f of x, and let's say that I want to take the derivative of both sides with respect to x. So I'm going to take the derivative of both the left and the right with respect to x. We're going to do that using the chain rule, right? That's the chain rule because I have some stuff going on the left-hand side over there. So when I take the derivative of the left-hand side, it's going to be the derivative of the outside function, g prime of f of x, times the derivative of the inside function, f prime of x, right? So it's the derivative of the outside function times the derivative of the inside function. That's the composition part of it. And the right-hand side, the derivative of x is just 1. Now, I am going to try to get f prime all by itself. So I am going to divide both sides now by the inverse, the derivative of the inverse. G prime of f of x. And what that gives me, clean it up down here a little bit, what that ends up giving me is f of x is now equal to 1 over G prime f of x. It's f prime of x. Yes, thank you. F prime of x is equal to 1 over G prime f of x. So by dividing both sides by the derivative of the inverse, we end up with this relationship between the derivative of the function as well as the derivative of the inverse, right? So we have two derivatives there. We have this relationship now going on between the two of them. And let's just see, let's practice, because this is, I think you have a problem like this in your homework. But let's let, I don't know if I put this on your notes or not, but let's let f of x be equal to e to the x. And therefore, if we let f of x be equal to e to the x, then what is the inverse of e to the x? What's the inverse of our exponential functions? Log functions, that's right. All right, and so e would have to be a natural log, right? Okay, and so the inverse of e to the x is the natural log of x, correct? How would I find that if I don't remember that I just did that 3 or 4 weeks ago? How do you find the inverse of a function? Right, we switch the x's and the y's. So if I had y is equal to e to the x, then that would look like x is equal to e to the y. Remember this? Okay, and then we would take the natural log of both sides. And we would have the natural log of x would be equal to y, right? So that's the inverse. Okay. So let's come back here. If we know that the function is e to the x, what is the derivative of e to the x?
E to the x.
E to the x. And what is the derivative of, and I wrote this wrong, I apologize. This should have just been g of x. Too many superscripts there. It should just be g of x because g prime of x is what? What is the derivative of the natural log of x? 1 over x. So if we use our idea from above that the derivative of the function is equal to 1 over the derivative of the inverse at the function, right? That's kind of what that thing above says. Then what we're asking is, does e to the x equal 1 over e to the x? Now, why is it 1 over e to the x? All right, so whatever f of x is, right? Or in s, yeah, whatever f of x is goes down here in the denominator, doesn't it? I'm composing the inverse derivative with the function itself, right? See that? Yes? Okay. So I would have 1, which is in the numerator. The derivative function is in the denominator, and the derivative evaluated at f of x is 1 over x, right? Okay, so does e to the x equal 1 over e to the x? Well, it does, right? Because 1 divided by 1 over e to the x is the same thing as multiplying by e to the x over 1. So we end up with e to the x, all right? So a inverse function, the derivative of our inverse functions, the derivative of a function and the derivative of the inverse function have this kind of reciprocal relationship with each other, don't they? Evaluated at the function itself, okay? So the rules or the properties theorems that we want to look at here said if f is continuous, if it's a function whose domain is on the interval of I, if f has an inverse function, then the following statements are true. Remember that not all functions had inverses. We had to create inverses, which were, we had to create one-to-one functions of our trig functions to make them have inverses, right? We had to restrict them. So if you have an inverse, the following is true, that f is continuous and the inverse is continuous on its domain. If f is differentiable on that interval containing c, and f prime of c is not equal to 0, then the inverse is also differentiable at c. And all that says below that, the derivative of an inverse function is the same thing that I wrote above. G prime of x is equal to 1 over f prime of g of x. Now that's in the opposite of the way that I wrote it, but remember that they go both ways, right? You can have both of them. In other words, the derivative of the function is equal to 1 over the derivative of the inverse at that function, as long as the denominator is not equal to 0. So let's look at this example here. This says we're going to let f of x be equal to x squared, and we are restricting it to only be the positive values for x. Why do you suppose I needed to restrict it? Because it's not one-to-one, is it? It fails that, what was that, the horizontal line test for a quadratic, right? So instead, I'm only going to look at the section of it now that's going to have the positive x values, okay? So we're looking at that portion of the function right there. That's going to be f. If the function is x squared, what do you suppose the inverse function is? Okay, well, that was a good guess. It's not the answer. So let's see if we don't know that, that's fine, we're gonna solve it, all right?
Like 1 over x.
No. All right, so 2x would be linear. That wouldn't be it. 1 over x would be rational. That wouldn't be it. Anybody have another guess? We're going to solve it, but anybody have another guess?
X squared? No, I said 1 over x squared.
Oh, all I heard was 1 over x. But that would still be rational.
Um,
All right, so y is equal to x squared, or in other words, when we switch them, x is equal to y squared. Take the square root of both sides. So therefore, the square root of x has to be equal to y. Okay. Now we restricted this to only the positive values, right? So I'm only interested in the positive square root of x and not the negative square root of x, okay? So we kind of don't avoid that issue. So g of x is now going to be the square root of x. That function looks like this. That's a square root function, isn't it? Okay. And we know that if we have the point 2, 4 on the function, then that same point, well, not that same point, what would be a similar point reflected onto the inverse function?
over 2.
4, 2. Okay. So, move this out of the way. That's how we got that. Now, let's come back over here. What is the derivative of f? what is the derivative of g?
1/2 x to the negative.
So 1/2 x to the negative 1/2. Now, what I want to know is, we have 2 points that we're going to look at. The first point, I want to know what is the slope of the tangent line for the function f at 2, 4. So if I'm using the point that falls on the function f, and that point is 2, 4, what is the slope at that point? That just becomes 2 from that derivative times 2, which is the x coordinate, or in other words, 4. Right? Tell me, what is the slope of the tangent line to the inverse at the point 4, 2? I want y'all to do it. Find the slope of the tangent line for the inverse, g, at 4, 2.
So g prime. Oh,
What do you get, 1/4? So they are reciprocals of each other, aren't they? Okay, that's the relationship between a derivative and the derivatives in the inverse of the derivative, right? That's what I'm trying to say about their points. That their slopes become reciprocals of each other. So maybe I can use that relationship to answer the next question. So this says that we're going to let f be defined by this third degree polynomial. I want to know what the value is at the derivative of its inverse. When x is equal to 58. The way that this is, what this is talking about is, so if we have the derivative of the inverse, this point is on, in other words, that's when x is equal to 58 on the inverse function, all right? That's what that portion of it is saying, that it's on the inverse function. Okay, well, what we're going to do is we're going to come back and we're going to look at the function itself, f. So let's take the derivative. So let's find the derivative. Which becomes what? 6 times 3x squared minus 11 times 2x. Or in other words, 18 x squared minus 22x. That's the derivative of the function x, correct? Okay. Now, what we just said is if I know what the value of a point is on the derivative of the function, then that's supposed to be related to the, I guess, the inverse point on the derivative of the inverse, correct? We're going to use that idea here. So the second component that they gave me is saying if I wanted to plug in 3 to the function or the derivative of the function, all right, I'm going to put 3 into the function, the derivative of the function we just found. And I would get 18 times 3 squared minus 22 times 3. Or in other words, I would get, what is that, 96? Okay. Making sure I did my math right, had the right problem up there. Okay. So I know that at the point 3, and it ends up being comma 58, that the value of the derivative is 96. And we can use then what we just said from above and say, okay, then for the inverse, that point that falls on the inverse, right? That point that falls on the derivative of the inverse. So I would have the inverse's derivative evaluated at 58 must be 1 over 96 is what that question is asking. And we're just basically saying that these two, that's the relationship between these two. We saw that just a minute ago, right? We knew what the slope was at a particular point on the function, and the slope at its inverse, on the inverse derivative of the inverse, was related in this particular way. So I maybe don't even have to go through and find out what the derivative of the inverse function is. I can just use the relationship that we've already established. That's all that point. That's all that question is really asking.
I'm a little confused about where you got 58 from. 58 was plugged in.
58 would be the x value on the inverse function. So if I know from the original function, if I know from f, we'll call it f. If I know that I have the point 358 on f, then on the inverse, I would have to have 58.3. That's where those two numbers are coming from. And I don't really ever have to do much with it. I'm just showing you that's how those are related at that point. Okay. So that's great. We have this relationship now between these functions as well as their inverses. But now let's see how that applies to our trig inverses. So we're going to let f be equal to sine x. And I'm going to let f inverse be equal to the inverse sine of x. Remember, inverse sine, we had to restrict the domain for inverse sine to be between negative and positive pi over 2, right? Negative pi over 2. for our inverse function to exist. And we're gonna kind of use those principles that we were using above, but the first thing I need to look at here is what is the derivative of f? Cosine x. Correct. The relationship that we know to be true from the theorem above said that I am going to now take, I have the relationship, I should just say it that way. Okay, so if I have f inverse, the derivative of the inverse is equal to 1 over the derivative of the function at the inverse. That's our relationship, right? I've already said that, okay? So if we're kind of looking at this, this is going to end up being 1 over, we already said that the derivative of f is cosine at the inverse, which would be inverse sine x. Okay? Now, before we go any further, because I ultimately want to know what is the derivative of the inverse function. That's actually what we are composing here. So I have a statement here that's written in both sines and cosines. So let's come over here and use our favorite thing about trig, and that is that the cosine of x. How can I relate cosine and sine together? Using what identity? Pythagorean, well, yes. Okay, I'm going to use the Pythagorean identity. All right. Yes, I could not use tangent, but it does relate it. And I don't know about the other one. Maybe the half angle is maybe what you're talking about. But let's use Pythagorean's identity because we like it. Okay. So I have sine squared x plus cosine squared x is equal to 1. And I'm going to rewrite this identity so that I can, I'm going to rewrite it solving basically for cosine. So I have cosine squared x would be 1 minus sine squared x. Take the square root of both sides, and I have cosine x is equal to plus or minus the square root of 1 minus sine squared x. So what I want to try to do is I want to be able to replace cosine with what we just solved this for. In other words, I'm replacing it so that I can take everything over there in my inverse function and rewrite it all in terms of sines. All right, that's why I did that one. Now I'm only interested in cosine being, so we're going from, we want the positive version of cosine. Okay, I want the positive version of cosine, so I can just get rid of the negative part right there. So we just said that I know that cosine x is also the same thing as the square root of 1 minus sine squared x, right? That's the identity part of this. So I can say 1 over, let's replace cosine now with 1 minus sine squared of x. But we are replacing x with the inverse of sine, right? Everywhere in here, we're replacing it with inverse sine. So it's all underneath the radical. So how do I go about simplifying this further? Let me rewrite this. Let's rewrite this so that we get rid of some of that, and it's a little cleaner under the radical sign. This is the same thing as 1 over the square root of 1 minus the sine, inverse sine x squared. Remember how we can take that square off of the trig in, right? I'm going to take it off of the word sign and I can put it to the outside because I'm technically squaring the argument or the angle. So I just rewrote it that way so that we can see what's happening here. Now, what do you see happening inside of that bracket? I have the sine of the inverse sine of x. But what happens when I compose a function with its inverse? I just get x, right? So this ends up giving me 1 over the square root of 1 minus x squared. And that is the inverse. That's the derivative of the inverse of sine. So what you're going to see when we look at all of these inverse trig functions, the inverse trig functions, notice that the derivative of its inverse no longer has any trig in it, does it? It's just got algebra stuff in it, x's and ones and square roots and stuff like that. All right. So what you have here then are all 6 trig function inverses. It's the derivative of their inverses. Now think about, I'm going to draw a line right here. Look to the left. We have the derivative of inverse sine, the derivative of inverse tangent, and the derivative of inverse secant. Memorize those. And then recognize the co-functions. Remember our co-function identities, right? Sine and cosine were co-functions of each other. Tangent, cotangent are co-functions of each other. Secant and cosecant are co-functions of each other. And so if you recognize now, how does inverse sine and inverse cosine, how are they related? They're related by just the sign, right, in that numerator. Okay. For inverse secant, it doesn't appear to be. I looked at 3 different books and they all say, well, there's just kind of a consensus on the derivative for the inverse secant, how they define it. This book will define it for x being positive, greater than 1. We're going to use x values that are positive less you greater than 1, okay, for the inverses. Okay. So those are the functions now we're going to use for the remaining problems that we have. So I want to know what is the derivative of the inverse sine of 2x. And we're all right that I can now go between inverse sine and arc sine, right? Okay. So I want to know what is the derivative of the inverse sine of 2x. Notice from And the inverse that you and I just derived a minute ago, our numerator was 1, all right? But just like with our natural log derivatives, we see that in general, what this is going to be is the derivative of the argument divided by 1 minus for sine, 1 minus the square of the argument. So in this particular case, y prime is going to be the derivative of 2x, which is just 2, over the square root of 1 minus 2x, all of that squared. Well, that's just 2 over the square root of 1 minus 4x squared. What do you think for tangent? All right, tangent. Notice that tangent is the derivative of the argument over 1 plus the argument squared. So for the derivative of the inverse of tangent, we have 3 over 1 plus 3x squared, or 3 over 1 plus 9x squared. So far, so good? Kind of straightforward now, anticlimactic after all of that work we did. Okay, how about the next one? The inverse arc sine square root x. Well, that's the same thing as inverse sine x to the 1/2. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2 divided by the square root 1 minus x to the 1/2 squared. Now we need to clean it up. So all of that except the 1 moves to the denominator. I would have 2x to the positive 1/2 times the square root of 1 minus x when I clean up underneath that radical sign. So I have 1 over 2 times the square root of x times 1 minus x. And you could simplify that by putting that, because they're both square root symbols, right? So I could move that inside or I could move it on the outside, okay? Either one. All right, now finally we have secant. We're going to use the positive value for secant, right? It had the absolute value bar on our x in the denominator. Well, the argument e to the 2x is positive, right? It's greater than 1 in essence. If we assume x is not greater than 1. So we are going to end up using our positive form. So for secant, the derivative of the argument, what's the derivative of e to the 2x? Times 2, that's right. So this is going to be 2e to the 2x. It's the chain rule because it's an e. Over, what we got up there? E to the 2x times the square root of e to the 2x squared minus 1. Just plugging it into the form. Now I can simplify because I have an e to the 2x in the numerator and the denominator. So I've got 2 in the numerator divided by the square root. E to the 2x squared is e to the 4x minus 1. And that's the solution. Okay, that's just applying the inverse rules. Questions on that? No, it's pretty straightforward, I think, if you're just plugging it in. Okay, let's look at these two separate examples here. So if we have the function f of x is equal to x inverse tangent of x over 2. Where did, and let's just make sure we remember, where does inverse tangent reside? It also resided between negative and positive pi over 2. So let's take the derivative of the function. Right, let's take the derivative of our function that we have right here. Well, that's the chain rule. So we have the first times the derivative of the inverse. So I'm just going to rewrite this one as x inverse tangent of 1/2 x. I can see that better. So when I take the derivative of f, I get the first times the derivative of the second. So this is our new one. What's going to be in the numerator here for inverse tangent? 1/2 over the original argument 1/2 x and then squared. So that set of parentheses right there represents the inverse tangent, and then we're going to say plus the derivative of the first. What's the derivative of x? All right, times the second, which is just inverse tangent of 1/2 x. Okay. Let me look. I think I put that in there wrong. That should be f prime, not f inverse. I thought that was wrong. So we want to evaluate the derivative at 2 square roots of 3. Okay, so let's clean up, or I don't really even have to, because I'm just going to evaluate it. If all I'm doing is evaluating, I'm going to plug in my values, right? So f prime of 2 square roots of 3 is what I'm looking at here. So this is going to be 1/2 times 2 square roots of 3 over 1 plus 1/2 times 2 square roots of 3 squared plus the inverse tangent of 1/2 times 2 square roots of 3. To answer this question, all I'm doing is evaluating it, so I'm not really going to spend my time cleaning it up any further. Y'all simplify that, tell me what you get. And we're dealing in radians here. So you should end up with the square root of 3/4 plus pi/3 for the exact answer. Okay? Questions? Okay, let's look at the next question that we have down here. Nobody has any questions over that? Okay. The next one says, let's not find an equation, let's just find the slope. All right. In the interest of time, let's just find the slope of the line tangent to the graph, secant inverse 2x at the point 1 pi/3. Okay. So with secant, we had to be careful about the absolute value, like which one am I choosing? Well, in this particular case, this is positive, right? So we're going to use our positive value for x. So the derivative of the derivative of g, it's going to be the derivative of the argument over the absolute value of the argument times the square root of the square of the argument minus 1. The 2 in the numerator cancels with the 2 in the denominator. We've already said we're looking for the positive values of x, or we're using the positive values of x, so we just end up with 1 over x times 4x squared minus 1. That's the derivative. What's the slope at the point? That's the derivative at x, right? 1 over 1 times the square root of 4 minus 1 is 1 over the square root of 3. Okay? And if I asked you to create the equation of the line, you would plug in the next part of it, y minus y1, blah, 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 right? Okay, the last problem I want to look at is this problem right here. Says that as the sun descends behind a 150-foot grandstand in a baseball stadium, the shadow of the stadium moves across the field, like you can see in the image. We want to let L be the line segment between the edge of the shadow and the sun. Theta is going to be the angle of elevation, and the shadow length is S. So we want to express theta as a function of the shadow length of S. Really, if I am looking for the shadow length, right, I know, or if I am trying to express this as a shadow length, theta as a function of the shadow length, then I can look at this and say, okay, well, I know 150, I know S, and I know theta. Because technically those are the relationships I'm looking for here, S and theta, the relationship between S and theta. And so using right triangle trigonometry, which one would I use to represent these three nodes or these three things? Tangent. So we would say then that the tangent of theta has got to be equal to 150 feet over S. Okay. Now, I want to compute d theta ds. That's the second part of this. I want to find d theta ds. The first thing that you ought to do though is we're going to take tan theta and we're going to solve it for theta, because theta is kind of hiding right there in that argument. And I'm going to take the derivative of theta, right, with respect to s. So let's rewrite this so that it looks like inverse tangent of 150 over s. Because I'm going to take the derivative, I'm actually going to go one step further and say inverse tangent of 150 times s to the -1, if you want to look at it that way. So we're going to take the derivative of theta with respect to s, or in other words, I'm just going to take the derivative of both sides. Implicitly is what we're doing here, taking the derivative of both sides implicitly. So the derivative of theta with respect to s is just theta prime, right? It's the same thing as taking the derivative of y with respect to x. It's just y prime. And the left-hand side, we're going to use our newfound formula. But this is the chain rule, right? This is the chain rule because I have S inverse down here in the argument. So let's take this off to the side and let's look at it for just a second. In the chain rule for inverse tangent of 150 S inverse, if we let U be that argument, in the inverse, then the derivative of the inverse tangent is 1 over 1 plus u squared, correct? Okay. And what is, if u is equal to 150 s to the -1, or 150 over s, whichever one you want to look at it as, what is u prime? Bring the -1 down, that would be -150 s to the -2. Right? Okay. All right. So what we're saying here is the chain rule says I'm going to take the derivative of the outside, which is 1 over 1 plus u squared. Well, u is the argument, times the derivative of the inside, which is the derivative of u, which was -150 s squared. So I can kind of clean that up. Theta prime is equal to -150 over s squared times 1 plus 150 squared over s squared. And now the question says, I want to know what is d theta ds when the shadow length is 200 feet. So to the nearest, let's see, if I'm gonna plug this in, I would have negative 150 over 200 squared times 1 plus 150 squared over 200 squared. What do you get? You should end up with you should end up with negative 0.0024 radians, because it's an angle, per foot. That's the same thing if you wanted to convert it to degrees as negative 0.138 degrees per foot. So if you were asked to interpret that, you might say, okay, well, when the shadow length is 200 feet, the angle of elevation is changing at a rate of negative 0.138 degrees per foot. Or maybe you would say the angle of elevation is decreasing at a rate of 0.138 degrees per foot, all right? Basically, it's just an application of our inverse functions. Okay,
Wait, how did you convert it to degrees?
I think I could just take the 0.0024 and convert it from, well, I'm converting from radians into feet, into degrees, right? So I would multiply by 180 over pi. Jonathan, you got a question?
Yeah, so I know you said we were like basically just plugging it into the formulas, but if we were doing that, how come